Afternoon, everyone. Here's my presentation on Activity 1 entitled Can a Colossal Titan Exist? So the question or the guide question is, given the maximum height a colossal titan can get, can its bone structure support its weight? So that's the question. So worksheet 1, instruction: perform the necessary actions required of in each exercise. If required to draw, use the space provided. If required to write an answer, provide one with as much detail as necessary. Use a ruler to draw two squares. So this is the first question. Use a ruler to draw two squares. The first square has sides of length 1 centimeter, and the second with 2 centimeter. Compute for and compare the area of the two. How are they related? Write down your solution answer beside or below your diagram. So the first square has a side of 1 centimeter. To find the area, so area is equal to s squared. That's the formula. So let's substitute the side. So area is equal to 1 centimeter squared. For the second square, which has a side of 2 centimeters, to find the area, so area is equal to s squared. Area is equal to 2 centimeters squared. So the area of the second square is 4 centimeters squared. So the explanation, the area of the first square with side measured 1 centimeter is 1 centimeter squared. The second square, on the other hand, with the side measured 2 centimeter has an area of 4 centimeters squared. As an observation, as the side increases, the area also increases. When the first square is scaled by a certain factor, the area of the second square is increased squared times the scaled factor of the first square. Let's proceed in question number 2. Use a ruler to draw two rectangles. The first rectangle has a width of 1 centimeter and a length of 2 centimeter. Multiply the dimensions of the first by 3 and use the resulting dimension to construct the second rectangle. Compute for and compare the area of the two. How are they related? Write down your solution answer beside or below your diagram. So the first rectangle has a side of 1 centimeter, its width, and the 2 centimeter, its length. So the area of a rectangle is equal to its length times its width. So the area is equal to 2 centimeter times 1 centimeter. So the area is equal to 2 centimeters squared. For the second rectangle, which was scaled by 3, so the area is equal to length times width. So 6 times 3. So the area is equal to 18 centimeters squared. The first rectangle with a dimension of 1 centimeter and 2 centimeters for width and length respectively, the area is 2 centimeters squared. However, the second rectangle, which was scaled by a factor of 3, has an area of 18 centimeters squared. Like in item number 1, as the dimensions of the first rectangle increases, the area also increases. Also, the area of the second rectangle is increased squared times the scaled factor of the first rectangle. Question number 3. Construct a right triangle with dimensions 15 millimeter, 20 millimeter, and 25 millimeter for the two legs and the hypotenuse respectively. Multiply the dimensions by 4 and construct the second triangle. Compute for and compare the area of the two. How are they related? Write down your solution answer beside or below your diagram. The first right triangle has a dimensions of 15, 20, and 25. So to find the area of a right triangle, we have the formula. Area is equal to 1/2 base times height. So area is equal to 1/2 times 15 millimeter times 20 millimeters. So area is equal to 1/2 times 300 millimeters squared is equal to 150 millimeters squared. So that's the area of the first right triangle. For the second right triangle, which has a dimension of 60, 80, and 100 millimeters. So the area is equal to 1/2 base times height. So area is equal to 1/2 times 60 times 80 millimeters. The area is equal to 2,400 millimeters squared. So the first right triangle with dimensions 15 millimeters, 20 millimeters, and 25 millimeters for the two legs and the hypotenuse respectively is an area of 150 millimeters squared. However, the second right triangle that was scaled by a factor of 4 has the area of 16 times higher than the first right triangle. The scaled factor is only raised to 2 or multiplied by itself. Therefore, the same observation with items 1 and 2. So question number 4, using the observations that you had for exercises 1 to 3, summarize the rule that describes what happens to the area of normal two-dimensional shapes as you multiply. So as the normal two-dimensional shape multiplied by or scaled by a certain factor, the area increases by squared of the scaled factor higher than the area of the normal two-dimensional shape. In short, the area is directly proportional to the squared of the scaled factor. Number 5, draw a cube with sides of length 1 centimeter. What is the surface area of the cube? Compute for the surface area of the cube and write your solution beside or below it. What is the volume of the cube? Compute as well for the volume of the cube and write your solution beside or below it. So to find the surface area, the formula is the formula for getting the surface area of a cube is 6 times s squared. So surface area is equal to 6 times 1 centimeter squared is equal to 6 centimeters squared. Then the volume V is equal to S cube. The volume is equal to 1 centimeter cube uh, by substituting the given side. So the volume of the cube of the given cube is 1 centimeter cube. Number 6, draw another cube with 3 times the dimensions of the first cube in exercise 5. What is its surface area? Compute for the surface area of the cube and write your solution beside or below it. What is the volume of the cube? Compute as well for the volume of the cube and write your solution beside or below it. So the surface area is equal to 6s cubed, substituting the side 6 times 3 centimeters squared. Surface area is squared. So surface area is equal to 6 times 9 centimeters squared is equal to 54 centimeters squared. So that's the surface area of the cube when scaled by 3. The volume is s cubed. Volume is equal to 3 centimeter cube. That is 27 centimeter cube. That's the volume of the cube, which is scaled by 3. Question number 7. Using your observations in exercise 5 and 6, what happens to the surface area and the volume of the cube as it's scaled 3 times? Without drawing, compute for the surface area and the volume of another cube scaled 4 times the first cube. What happens to the surface area and the volume compared to the original cube? How about for the cube scaled 5 times? So letter A for question in A. As what I have observed, the surface area of the cube as it was scaled 3 times is that it is square of the scaled factor higher than the original cube, which means it is 9 times higher than the original surface area. The volume, on the other hand, is cube of the scaled factor higher than the volume of the original factor. For question in B, the surface area, so here's the answer. The surface area is still square of the factor being scaled higher than the original cube. The scaled factor is 4, then the surface area is 16 times higher than the original surface area. Nevertheless, the volume is still cube of the scaled factor higher than the volume of the original cube. For C, question C, for a cube scaled 5 times, the surface area and the volume are observed the same as it was scaled 3 times and 4 times. The results or observations remain the same for surface area and volume. Question number 8. Write down 2 rules describing how the surface area and the volume are increased as the dimensions are scaled by a factor. The first rule should be about the surface area of the three-dimensional figure increases as the dimensions are scaled by a factor. The second rule should be about how the volume of the three-dimensional figure increases as the dimensions are scaled by a factor. First rule, when the dimensions are scaled by a certain factor, the surface area of the three-dimensional figure increases by the square of the scaled factor. Second rule, when the dimensions are scaled by a certain factor, the volume of a three-dimensional figure increases by the cube of the factor being scaled. Question number 9, translate your description into a mathematical sentence and test it for validity with other figures. Does it apply? Can your rules describe the increases in the surface area and volume of other figures when their dimensions are scaled by a factor? So for surface area, let y be the surface area of a figure, x be the scaled factor. So y is equal to k, which is constant, times x squared. For volume, let y be the volume of a figure, x be the scaled factor. So the formula will be y is equal to kx cubed, where k is a constant. So here's the proof for a rectangular prism which has a length of 3 centimeter, width of 1 centimeter, and a height of 2 centimeter. So for the surface area, using the formula in getting the surface area. So surface area is equal to 2 times length times width plus length times height plus width times height. So the surface area is equal to 2 times bracket or parenthesis 3 plus 6 plus 2. So surface area is equal to 2 times 11. So 2 times 11 is equal to 22. So the surface area is 22 centimeters squared. For the volume, that is length times width times height. So the volume is equal to 3 times 1 times 2. That is 6. So the volume of the rectangular prism is 6 centimeter cube or cubic centimeters. So when scaled by a factor of 3, the surface area is equal to 2 times length times width plus length times height plus width times height. So that is 2 times 27 plus 54 plus 18 is equal to 99. So 2 times 99 is equal to 198 centimeters squared. So the surface area of the rectangular prism when scaled by a factor of 3 is 198 centimeters squared. For the volume, length with the formula, volume is equal to length times width times height. That is 9 times 3 times 6. That is 162. So the volume of the rectangular prism when scaled by 3 is 162 centimeters squared. So using the formulated equation for the surface area, y is equal to kx squared. So this is the formula or the formulated equation. So y is 22. Ayun na, yes, surface area 22 siya. So 22 is equal to k times 1 squared. So k is equal to 22 over 1. So that is 22. So k, the constant, is 22. So y is equal to k x squared. Y is equal to 22 times 3 squared. So the 3 is the scaling factor. Y is equal to 22 times 9. That is 198. So the surface area of the rectangular prism is 198 centimeters squared, which is equal to its surface area when the formula using the rectangular prism is used. So for the volume using the formulated equation, y is equal to k times x cubed. So y is equal to 6, substitute, and x is equal to 1. So 6 is equal to k times 1 cubed. So k is equal to 6. So for to get when it's scaled by 3, y is equal to k times x cubed. Y is equal to 6 times 3 cubed. That is 6 times 27 is equal to 162. So that's the volume of the rectangular prism when scaled by a factor of 3 is 162 centimeter, which is equal to the first solution or the first answer. Excuse me. So therefore, the rules can describe the increases in the surface area and volume of other figures when their dimensions are scaled by a factor. Number 10, assuming that the same rule applies to irregularly shaped objects with a known dimension, say a human with a known height, the area covered by the skin of a human would be a surface area. If you increase the height, how would you expect the surface area of the skin to increase based on your formula in exercise 9? Based on the formula in exercise 9, if the irregularly shaped objects with a known dimension or its height is known, then its surface area or its skin will increase by a square of the scaled factor because of its direct proportionality. So if the height is scaled by 5, then the skin will increase 25 times the original. 11. Using the same concept in exercise 10, how would you expect the volume to increase as the height increases? Volume can be attributed to the person's weight. If a boy who is 165 centimeter tall weighs 60 kilogram, assuming that all other external factors are similar to the examples, how would you expect his father, who is 182 centimeter, to weigh? So using the same concept in exercise 10, the volume will increase as the height increases since the volume or weight is directly proportional to the height. So here's the proof. The sun stands for 165 centimeter when weighs 60 kilograms. So let W be the sun's weight and H be the sun's height. So W is equal to K times H. W is equal to 60, which is the weight of the sun is equal to K, which is the constant, and 165 is the height. So K is equal to 60 over 165 or 4 over 11. So when K is equal to 4 over 11, W or weight of the father is equal to 4 over 11 times 182. So the weight is equal to 66.18 kilograms. Therefore, the father's weight is approximately 66.18 kilograms. Number 12, in the cartoon series Ben 10, Ben stands around 135 centimeter high and weighs approximately 27 kilogram. When needed, however, he can morph into nanomech, a human nanochip hybrid that stands 2.5 centimeter tall. How would you expect nanomech's weigh? What would you expect nanomech's weight to be? Given that Ben stands 135 centimeter and weighs approximately 27 kilogram, his weight is 5 times lower than his weight. So when he morphs into a nanomech, nanomech's weight will also decrease 5 times than his height since height and weight are proportional with one another. So here's the proof. So let W be Ben's weight in kilogram, H be Ben's height in centimeter. So W is equal to KH, where K is constant and H is the height. So W is equal to 27 is equal to K times 135. So K is equal to 27 over 135 or 0.2. So when K is equal to 0.2, the weight of the nanomech is equal to 0.2 times 2.25, that is 0.05. So therefore the weight of the nanomech is zero point 0.5 kilograms. For worksheet 2, question number 13, using the height and the surface area relationship of the father and the son in exercise 11, by what factor is the father's surface area larger than the son's? So let H be the height and W be the weight. Sun's surface area is equal to height times weight, or H times W, or height times weight. That is 165 times 60 is equal to 9,900. For father surface area, height times weight, that is 182 times 66.18 is equal to 12,044.76. To get the factor, father surface area divided by sun's surface area, that is 12,044.76 over 9,900. So the answer is 1.216642 or 1.22. Therefore, the father's surface area is 1.22 times larger than the son's. 14. Based on 13, how would you compare the surface areas of the cross sections of the bones from the father and son? It is mentioned in the activity that on Earth, the density of the bone increases based on the size, surface area of the perpendicular cross-sectional area of the bone. Based on 13, considering that the father is taller and heavier than the son, therefore the size or surface area of the perpendicular cross-sectional area of the bone of the father is larger than the son. 15. The colossal titan in the movie Attack of the Titan has a height of 60 meters. Using the measurements of the father and the son and your rule on the increases in volume, what is the approximate weight of the colossal titan? So let W be the sun's weight, H be the sun's height. Given H is equal to 165 centimeter and W is equal to 60 kilograms. So W is equal to KH or K constant and H is height. So 60 is equal to K times 165. So K is equal to 60 over 165 or 4 over 14. For the colossal titan, given the height is 60 meters, that is 6,000 in centimeter. So weight is where we are going to find the weight. So substitute the value of K to get the colossal titan's weight. So W is equal to KH. So W is equal to 4 over 11 times 6,000. That is 24,000 over 11. So W is equal to 2,181.82 kilograms. Therefore, the approximate weight of the colossal titan is 2,181.82 kilograms. 16. Based on the observation you have on 13, by what factor should the cross-sectional area of the bones of the colossal titan increase in comparison to the father and son to support its weight? So let H be the colossal titan's height and W be the colossal titan's weight. To get the colossal titan's surface area, that is SA is equal to weight times height or H times W, that is 6,000 times 2,181.82. That is equal to 13,090,920. So in comparison to Sun, the colossal titan's so colossal titan surface area divided by sun surface area, that is 13,090,920 over 9,900, that is equal to 1,322.32. So in comparison to father, the colossal titan surface area over father's surface area, that is 13,090,920 over 12,044.76, which is equal to 1086.86. Therefore, the cross-sectional area of the bones of the colossal titan should increase by 1322.32 in comparison to the son and 1086.86 in comparison to the father. 17. The surface area of the cross-section of the bone on the legs of the son on 13 is approximately 3.141 centimeters squared. If the height of the colossal titan is 60 meters, what is the necessary area of the cross-section of the bone on the legs of the colossal titan B to support its weight? So given the surface area of the cross-section of the bone on the legs of the sun is equal to 3.141 centimeters squared, the colossal titan's height is equal to 60 meters or 6,000 centimeters. So sun's height is equal to 165 centimeter. So let L so be the surface area of the cross-section of the bone on the legs of the sun, and H be the height of the sun. That is L, or the equation is L is equal to HK, where H is a where K is a constant. So 3.141 is equal to 165 times K. That is K is equal to 3.141 over 165. That is also, so the K is equal to 1,047 over 55,000. To get the surface area of the cross section of the bone on the legs of the colossal titan, L is equal to HK, that is 6,000 times 1047 over 55,000, which is equal to 6,282 over 55, or 114.218, or 114.22. Therefore, the necessary area of the cross-section of the bone on the legs of the colossal titan to support its weight is approximately 114.22 centimeters squared. 18. On manga, it was seen several times that approximately the size of the bones on the legs of the titan is 8 humans. If a typical human has 36 inches, 91.44 centimeter of waistline, what is the approximate surface area of the cross-section of the bone of the titan? So given 8 humans, the size of the bones on the legs of the titan. So 91.44 centimeter, the typical human's waistline. So 8 times 91.44 is equal to 731.52. That is the diameter and the radius. To get the radius, we have to divide 731.52 by 2. That is 365.76. To get the surface area of the cross section of the bone of the titan, so area is equal to pi r squared. That is pi times 365.76 squared. So the area is equal to 420,283.45 or 422,283.45. Therefore, the surface area of the cross section of the bone of the titan is approximately 420,283.45 centimeters squared. 19. From the previous exercises, can a colossal titan exist? Why? Why not? So based on the previous exercises, I don't think that a colossal titan can exist. It's quite impossible to imagine the existence of this giant creature because of its bone structure cannot support its weight. The cross section of its bone cannot compensate its weight. 20. Godzilla is portrayed to weigh 50,000 tons at 150 feet. Can it exist? Why or why not? If we are going to compare the Colossal Titan with the Godzilla, the former weighs approximately 2,181.28 kilograms and stands 6,000 centimeter high. The latter, on the other hand, weighs 50,000 tons, that is 45,359,237 kilograms, and stands 150 feet, that is 4,572 centimeter. If it's impossible for the Colossal Titan to exist with its dimension, so how much more the Godzilla? Godzilla's weight is incredibly huge in relation to its height. Therefore, like a colossal titan, Godzilla's existence is also impossible to imagine. And that's the end. Thank you.